Hello, welcome back to my lecture series. Today's topic, we're going to talk about the mathematics of perspective, as well as this concept called empathy, for um, and how they're related to like what we've learned so far. Okay, so I'm Professor Wu. Let's get started. From our previous lecture, I don't know if you remember the lecture on, I guess, how to get what you want in life. Basically, we were using different vectors to reach a certain goal. Right? We have different vectors. We're hoping to reach some kind of goal. Now, if you look at all these different approaches, right? You could go this way, right? You could go this way, this way. You could also go this way, this way. So there are many ways to reach our destination. But it is, if you just look at it, it's perhaps the easiest if you simply pick complement and humor, right? Using this vector specifically, it kind of gets complicated because you don't know exactly how long you're supposed to be. Like here, if you use this, you know exactly you're supposed to go 1.2 and exactly zero point 0.6. So it's very easy to figure these out. However, it's not obvious where you're supposed to stop in order for you to reach this goal using this vector. So the idea is that hopefully you notice using these two is the easiest way to figure out the coefficients. And the reason is because, well, they're perpendicular to each other. Right? They're perpendicular to each other. Therefore, the direction here doesn't impact the direction this way at all, right? So you can just kind of look at this direction on its own and know exactly where to go, and then look at this direction on its own. Having perpendicular bases really helps, right? It makes finding the coefficients quite easy. Um, in linear algebra, right, these perpendicular vectors are ideas from our what we learned from geometry, and specifically in 2 or 3 dimensions. But in linear algebra, we deal with higher dimension. The general idea of perpendicular in higher dimension, we call it orthogonality. Okay. So let's go over some like just basic vocabulary so we can kind of talk about them. So if two vectors are perpendicular to each other in high dimension, right, in any dimension, it's called orthogonal. So the general idea of like being perpendicular to each other in high dimension is orthogonal. And if you have a set of basis vectors that are orthogonal, then you have an orthogonal basis, right? Orthogonal basis automatically means that if you have n number of vectors, right, you automatically span n dimensions because all n of them have nothing to do with each other. And now, if you have if you have a set of bases that are orthogonal and they have a length of 1, so if they're orthogonal and they have a length of 1, then we call it orthonormal basis. So this is the ideal basis. This is the basis that you really would like to have. Oh, right here. Orthonormal base is the best possible base you can have. Now, we'll later see why they're so useful. In fact, this idea of like basis, like orthonormal basis, can be used to model how we view the world differently. Orthogonal vectors have very special properties. So, majority of this class is for us to understand what they are as well as their properties. One of the first property is that when two vectors are orthogonal, their inner product, so their dot product, is always zero. Always zero. So that's a really useful property, and you need to remember that. In the figure here, right, we have two vectors, v1, v2. If we take the inner product, then because they are perpendicular, it will be zero. Okay. So right now, I want you to pull out NumPy really quickly, and just this is two-dimensional space, and just do a dot product, and you will see that you will get a 0. Now, this is 2-dimension, but in higher 3-dimension, notice that they're also perpendicular, and therefore when you take the dot product, so just take the dot product, and you'll see. I pause the video. You should just do this really quickly to convince yourself that the dot product, if the two vectors are perpendicular, are 0. Property number 2. Given an orthogonal basis, you can convert it into orthonormal basis. Orthonormal basis. So if these 3 vectors are perpendicular to each other or orthogonal to each other, then you can always convert it from orthogonal to orthonormal. What's the difference? Remember, orthonormal are just orthogonal bases. The only thing is you take one extra step of normalizing each vector. And when I say normalizing, I mean turning into a length of 1. Right now, hopefully you still have your Python open. Just remind yourself how to convert them into a normalized version. Right? After you convert them into normalized version, you can essentially see that v1 normalized dot v2 normalized is going to be 0. Right? All right, so I give this a try, really quickly, and then we'll move on. Here's the solution. All right, here's the next property is that how do we tell if a set of basis vectors are orthogonal? So is there a test for that? And the answer is yes. Well, if you have v1, v2, v3, right? So the obvious test is, well, if v1 dot v2 and v1 dot v3 or v2 dot v3, all of them should be 0. Right? But you can see this kind of gets cumbersome, because if you have a lot of basis vectors, then you got to do like every single combination of them, right? I think the combination is like n choosing 2. So it's quite a bit, a lot of combinations. So this is one way to do it, but a better way is you can actually just stack them together. Let's say you have v1, v2, you're stacking them horizontally. And after you stack them together, notice how if you just multiply v1 transpose v, you will calculate every single combination automatically, right? Let's see how this works. If you have v1 transpose v2 transpose v3 transpose, and then you multiply by the transpose version, v1, v2, v3. If you were to multiply them together, you're going to get v1 transpose v1, v2 transpose v1, v3 transpose v1, v2 transpose v2, no, v1 transpose v2 transpose v2, so on and so forth. The point is, this automatically calculates the inner product for every single possible combination, right? And therefore, as long as you have the top and the bottom of the diagonal to be 0, then you essentially have an orthogonal basis. So this is the easiest test in order for you to test them, whether they're orthogonal or not. You stack them and just multiply by its own transpose. Now, we can also run a test for orthonormality. So previously, it's just orthogonal. We check if they are perpendicular to each other. But now, orthonormality is we are simultaneously checking if they are perpendicular and they have a length of 1. Right? All the bases are length of 1. So the way we check for that is exactly the same thing. We just stack them together and then simply multiply VV transpose. If the diagonals are all 1s, off diagonals are 0, then that's it. That's how you can check if they're orthonormal. Well, like right now, you're just learning the definition and their properties, but we'll get to how we'll use them in a little bit. Let's practice this. Are these vectors orthogonal or orthonormal? Okay, so let's run this test. Pause the video and do this. If they are not orthonormal, then you need to convert them into orthonormal, then use them. Okay, here's the solution. Pause the video, you can check it out. All right, property number 5. Man, this is definitely lots of properties. And this is the most special property. It's that if you have a square matrix U, right, that consists of orthonormal vectors. So if you have orthonormal vectors like U1 transpose U2 transpose U3 transpose, right? Now, if you have these vectors as orthonormal, so orthonormal basis vectors, then you don't need to calculate the inverse. This is the extra useful one, is that if you simply calculate the transpose, it is the same as the inverse, right? And this is for obvious reasons. Let's say you have U1 transpose, U2 transpose, U3 transpose, right? And then the vectors are U1, U2, U3, right? So this is the transpose of each other, right? They're transpose of each other. Now, you notice how when U times U, because it's orthonormal, the length is equal to 1. But when U times 2, it's 0. U times 3 is 0. And then it's basically 1 off the diagonal. Therefore, it's an identity matrix. This tells you that orthonormal bases are very special because you don't need to calculate inverse anymore. Yes. You just know by performing a simple transpose. Okay. All right. Let's practice this property. We have the U and verify. First, you want to do and verify that U transpose is actually identity. And then you want to compute U inverse using the 2 by 2 trick. Remember how we calculate that? And then confirm that it is equal to the U transpose. Okay, so we learned this previously. Determinant of A. Okay. Also, here's the solution. You want to pause the video and then do it. All right. Now we're ready to move on to the goal of today. Like all these is to build you up to kind of know what we're talking about. Before we continue, let's do another review for projection. Remember we did projection last time, right? So if we have V here, you're trying to project it onto the vector U, so you form this perpendicular area. If we want to find this distance from here to here, alpha, then alpha is simply V transpose U hat. So V multiplied by the normalized version of V. V multiplied by the normalized version of U. And once we know alpha, we simply multiply the normalized version of U by alpha, which gives us this point D. So this is how we got the equation D and alpha. And if we simply plug alpha into here, then we have a direct equation of how to find a projection. So the projection is essentially U hat times V transpose. All right, let's just quickly practice this. Given this figure here, see if you can find the point of projection. And then once you find a point, why don't you visually see if the numbers make sense, right? All right, pause the video. Here's the solution. All right, so now we're ready to move on. So far, when we learn about projection, notice you're projecting onto one dimension. That's all we've been doing so far. But of course, we don't just possess one basis vectors. We have like hundreds of thousands of basis vectors. So the question is, when you perform a projection in a higher dimension down to like two, three, four basis vectors, how do you do it? Like for example, let's move beyond two dimension, right? Two dimension, and let's move on to three dimension. Here's specifically. So we have a point here. So this point is in 3D. However, your span is red and green. So you're on the 2D. So you're currently on this 2D area. So when you project this point down, right, you're going to project down to a point in 2D. So how do you do that when you have more than one basis vector you're projecting down? Well, projecting onto multiple vectors is similar to just projecting to one. What we do is we simply project down to the first one. So let's say we have u1 and u2. So we have two vectors and we're projecting x down to these two basis vectors. Okay, so if we project onto two of them, what we do is we just project onto the first one. We get a projection. We project onto the second one, so we project first one and then second one, and we simply add up the results. After we add up the results, is the combination of the two of them, which will give us this point here. Okay, so that's the general idea of how it works. And over here, notice I changed the notation. After projection is capital U. So this is projecting onto not just a single U, but a bunch of them. All right, let's try this exercise yourself. We have um, we have X, and we're trying to project onto U1 and U2, which capital U, wait, yeah, which capital U is equal to this. So let's try to pause the video and see if you can find the resulting projection. Right, this will be the resulting projection, and do as much calculation by hand as possible. But if it's too complicated, feel free to just use Python. Okay, all right, let's try this. I provide the solution here for you as well. So projecting onto each basis one at a time is a pain. So what I taught you guys so far is if there are two bases, just project onto each one of them and add up the result. Implying that if you have 3, 4, 5, 6, 100, you have to project down to 100 times. But as you've learned from linear algebra, very often we can batch up these processes. Okay, so if we want to batch this up, for example, well, remember, you project. So this is the projection down to U1. This is a projection down to U2. Now remember, when you have a dot product, this is just a number. So this is alpha 1, alpha 2, right? Remember how we deal with things that looks like this. If we have alpha 1 V1 plus alpha 2 V2. Well, we saw this before. This is equivalent to we combine the vectors V1, V2 and alpha 1 alpha 2, right? So we can pull the coefficients out. Okay, so in this formulation is the same. These are just coefficients, so we can pull them out. So notice we have u1 u2. Now I've combined them into a single matrix, and then I pull the coefficients out. Another thing we can further simplify is that when you do a dot product, you can flip the order. So x could be on the outside now. Now we have x. Well, x could actually be pulled out. Notice here. And therefore, what we end up having is that this right here is a U matrix, and this is a U transpose matrix times x. Therefore, if we are trying to calculate the projection down to multiple of them, the easier equation is simply XU U transpose, right? So you stack it this way. So you can imagine if you have 3 dimensions, then you'll be u1, u2, u3, right? So that'll be u, but this equation will stay the same. So it doesn't matter how many dimensions you're trying to project down to, you can always just rely on this equation and get the final solution. And this is much easier than if you try to project the vector one at a time. All right. So over here, we do it this way. Notice how I stack them as u, and then I simply take x times u transpose. X times u transpose. And it gets the same result. So it's calculating exactly the same thing as we just did before. Now, this is great. This is great. However, this doesn't really always work. There's some problems to it. And the problem is that this approach only works if if we have some special properties. So over here, for example, I'm trying to project x down to the two vectors. The two vectors looks like this. If you try to do this, it's actually going to give us the wrong projection. Instead of here, it will give us something like here. So it will give us the wrong projection. So why is it that it worked the first time, but it's not always working depending on the basis vector? And it goes back to that 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 the basis vector can only get project down if and only if you have them as orthogonal basis vectors. In fact, it's not just orthogonal. You need them to be orthonormal. If you have orthonormal basis vectors, then it will work. So over here, we're giving these two, right? If we actually try to do the projection, notice that the projection is not 1, 1, 0. Even though it's supposed to be 1, 1, 0, right? You can see 1, 1, 0. But because the basis vectors are not orthonormal, then when you follow this whole process, you're going to get the wrong result. Wrong result. So that's an important factor you need to know. You cannot really perform projection in a high dimensional space unless they are orthogonal. I mean, unless they're orthonormal, in fact. That's the only condition. So, okay, another thing I want to talk about is now we know how to do projection. Oh, by the way, you cannot have orthonormal basis. If you don't have orthonormal basis, you cannot perform projection to a high dimension space. So normally what we do is we have our basis vectors that are not orthonormal. They're random in different directions, our bases. There's a technique that converts these bases of random directions into perfectly orthonormal. Right. So you can do this through either Graham-Schmidt or Eigen decomposition. So there are two ways to convert your bases into orthogonal bases. So obviously, not all bases are going to be perfectly nice. However, you can do a conversion, and once you do a conversion, then you can do projection after that. And in linear algebra, they definitely learn Graham-Schmidt, but Graham-Schmidt is not used very much in machine learning. It's used, just not that much. So therefore, we're going to cover just one of them, which is the Eigen decomposition. Okay, so what is projection onto orthonormal vector doing? Well, let's say we have 3 points, x1, x2, x3. And we have an orthonormal basis right here and right here. Notice they are perpendicular, right? So they're orthonormal and their length are 1. Okay, so we have these 3 points. If we perform projection here, We perform projection. We perform projection. What is happening? Well, remember, if we do a projection, we can find the alpha value. Alpha value, right? Alpha 1 over here will give you alpha 3, and then over here will give you alpha 2. So you know the alpha value. And okay, and let's say that we have these 3 points, x1, x2, x3, which is stack is just matrix X. And we know that um, the first basis is mu1. Okay, I'm going to call this as u1. So if we want to find the distance between here to here, it's simply x1 times u1 normalized. So we can find the distance here, and that will give us alpha 1. Now, if we want to find the distance to the second one, x2 u1 hat, that will go here, alpha 2. This gives you this distance. So we know how to find the distance. Okay, what is the point? The point is that this axis, the number of these axes correspond to the alpha values. So, for example, x1, right? If you just look at the normal axis, this is the normal axis. It's at roughly 1/2 and 3. This is the coordinate for x1. However, if you change the coordinate system into this and here, this is a new coordinate system. And in this coordinate system, what is the coordinate? Well, according to this coordinate, you will have to do a projection. So this right here is alpha 1. And then you have to do a projection this way. So this is beta 1. So previously, this was 0.5 and 3. But in this other coordinate, what we have is alpha 1 and beta 1. So the point I'm trying to make is that you if you have a particular point in its original coordinate, it's actually there are other ways to represent this exact same point in other coordinates, right? In other coordinates. So this right here is another coordinate, and then over here, right, is yet another coordinate. So there are many, many, many different ways to represent the exact point. Like the point doesn't change, but the perspective changes. All right. So the point I'm trying to make is when you're projecting down to an orthonormal basis, that's not the standard. Like this would be the standard basis. You're projecting onto a non-standard orthonormal basis. It's um, equivalent to translating what this point is for another from another perspective. And specifically, you know the coordinate. The coordinate is you project down to this vector, which will give you alpha 1. And then you project onto the second dimension, which will give you beta 1. So you know the coordinate through projection. Hmm? So let's say we have these 3 points. Now, if we simply perform projection, so we multiply u1, u2, u3, we're going to get the coordinates of alpha 1, alpha 2, alpha 3. So this give us all the x values. And then if we project down to u2, which is this direction, u2 hat, then we're going to get all the beta values. Okay, so this is how this is kind of like how we can model perspective mathematically. Different perspective have different ways of viewing the same thing, right? So this is one perspective. You can view this point based on this perspective, or you can change your perspective. And from this perspective, x1, exact same point, it has not moved, would have a different coordinate, right? So I hope hopefully you get the point, but I think it's easier if you give this exercise a try. So let's say you have this is your axis, so you have the standard axis, and you have a friend that look at things differently, and their axis looks like this, okay? And these are the two orthonormal bases. I already normalized it for you. So what is the x1 coordinate for you? For you versus what is the x1 coordinate for your friend? So why don't you see if you can understand everything we talked about, incorporate them, and see if you can solve this particular problem. Okay, I'll leave the answer here as well. So the idea of perspective then allows us to, if we can mathematically model perspective, a different perspective, then we can mathematically model empathy. So empathy is the ability to understand the feelings and thoughts from others' perspective. So different perspective could be represented as different orthonormal bases. You have one orthonormal basis, you rotate it a little bit, it becomes a different orthonormal basis. Therefore, given a piece of information, the way x, the idea of a point, is encoded in your brain is vastly different how it will be encoded in someone else's brain. And this is because we basically have different orthonormal bases and different coordinate system. Right? So mathematically, given a piece of information, we can represent the perspective with an orthonormal basis of u. So, so you can represent as u, and then you can get the coordinates simply by multiplying x by u. So this is the new coordinate. Okay? We can represent your friend's perspective this way. So if you have a coordinate, your friend has a coordinate, we can basically get this for this particular point, what is the coordinate for you and what is the coordinate for your friend. So let me define empathy mathematically. Empathy is a willingness to identify the orthonormal basis of others and project your point onto their basis. So what's happening is you have some point. What this is how you understand the world. And then what happened is you can essentially understand their matrix and figure out how they understand the world. Right? This right here. And your willingness to do that is the key. And there's actually a lot of advantages to being able to see things from their perspective. So I mean, we can get into it, but let's look at it geometrically. I think geometrically is the easiest way. Let's say we have um, let's say we have two axes, so x y z, right? Let x y z. So that's let's say that this is your axis, and then we have the axes of your friend. So both of them are orthonormal. We'll start with that. And and I I actually think, one second. I think you can't really see it. It's easier to see this if we have, let's see. Here we go. Yeah. Let me see if I can zoom in. Insert, no, view, zoom. Oh, there we go. All right. So let's say that we are, our goal is to rotate these points along the z-axis of your friend. Right. So from your friend's perspective, I mean, from your perspective, it looks like a really complicated rotation. However, from your friend's perspective, it's quite easy. It's just rotating around z-axis. So we know how to rotate points around a z-axis. So it's easy for your, if you have your friend's perspective, But it's very hard to understand this from your own perspective. Like, how do you figure out all the points to rotate along like a axis that you're not used to? So, so if you're able to project your points into the perspective of your friends, and then you can rotate around the z-axis really easily. Then, because we know how to do that. So the idea of being able to see things from other people's perspective actually simplifies your life, because certain things that doesn't make sense will just start making sense if you look at it from their perspective. And not only does it make sense, it's like really easy and obvious. So the key, like, therefore, is to shift your perspective. And if you can shift your perspective, you can essentially achieve what seems to be really difficult things easily. And to achieve this effect, right? So if you want to rotate it around z-axis, if we want to, like, what we'll normally do is we take our data, multiply by a rotational matrix, right? So this is what we'll normally do. However, we don't want to rotate it along our own z-axis. We want to rotate it around their z-axis. So what we do is we essentially convert our coordinate into their coordinate by multiplying by their basis vector. So this is the orthonormal basis vector here, orthonormal. And then we rotate. All right. So this give us this we are looking at it from their perspective, and then we start rotating in their perspective along the z-axis. And then once you're done, if you have multiple points, so like this is just one point, right? If you have multiple points, then you can stack them up together like this. So if you have a lot of points, you just multiply and you automatically rotate them along the z-axis. However, if you can't just like show that, because if you just show the result of this, it will simply look like you're rotating along the z-axis. You need to translate it back again. So so remember, you have to undo the perspective transformation. So you take a point, change it into their perspective, you rotate, which is here, rotate, and then you multiply by the inverse. So you undo their perspective to go back to your own perspective. All right? Does that make sense? You start from your perspective, you shift to their perspective, you rotate, and you undo. And what is interesting about the undo is that the inverse is the same as the transpose, because this is an orthonormal basis. Because this is, and therefore this equation allows you to change your perspective, do something while in that perspective, and then translate it back to your own perspective. And this is a really really cool, like really really cool way of understanding perspective and empathy. Right, that you're essentially, in order for you to understand someone, this is essentially the equation for empathy. You understand someone, like manipulate some idea based on how they think, and then you translate it back into your own understanding. So 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 yeah so for the rest of the class, this is the code that actually generates this. Your goal is to get this to run and see if you can get it working, right? I think I provided you some code, and then you can essentially build on top of it and see if you can get this to work, where you change to their perspective and display it in your own perspective. All right, so I guess that's it for today. I will see you in the next lecture.